All right, this video we're going to try to squeeze in these two solutions here for these two linear first order initial value problems. So the first one here, let's restructure that so it's in its normal form. We'll divide by x. Always have warning bells going off when you divide by x. You got to be careful about discontinuities there and how that affects your domain. All right, so let's see here. We'll multiply by our integrating factor. And this means we want the negative 3 over x row. We want that to be rho prime. So let's do that off to the side. We want rho prime to be equal to negative 3 over x row, which means d rho dx is equal to negative 3 over x row. D rho over rho is equal to negative 3 over x dx. And so integrating, we'd have natural log absolute value of rho, and on the right hand side, negative 3 natural log absolute value of x plus, call it c1. And we'll do our exponential function strategy again, same type of thing, e to the negative 3 natural log absolute value of x times, we'll say e to the c1. This one up here, you can see the natural log and that exponential function will interact, but I have to have that e to a natural log, so let's rewrite this. Rho equals, we'll call it c2 e to the natural log absolute value of x to the negative third, which tells me then that rho can be c2 just absolute value of x to the negative third, or we'll absorb that in a final constant c3x to the negative third. All right, so there is our integration factor. So let's multiply that. We've got we did c3 by the time we were in the end there. c3x to the negative third y prime minus 3 over x c3x to the negative third y equals c3x to the negative third x squared. All right, like always, those constants, we can divide those constants out. We have x to the negative third y prime minus, let's see, 3x to the negative fourth y equals x to the negative first. And so on the left-hand side, that is the derivative of x to the negative third times y, right? So x to the negative third times y prime plus, and then the derivative of x to the negative third would be negative 3x to the negative fourth y. And so that would be, we'll do our separation, integrate both sides. So we have x to the negative third y equals natural log absolute value of x plus c, and finally multiplying through by x cubed, y is equal to x cubed times the natural log of the absolute value of x plus c. All right, now we have our initial condition, y at negative 3 is equal to 10. So let's go over here. Y at negative 3 is equal to 10. I guess we can leave all that on there. Let's see. So we have negative 3 cubed times the natural log of the absolute value of negative 3 plus c should be equal to 10. So the natural log of 3 plus c should be equal to negative 10 27ths, and then c would be negative 10 27ths minus the natural log of 3. And so finally, y at x is x cubed times the natural log of the absolute value of x, minus 10 27ths minus the natural log of 3. Now one thing I did not write down for myself is the domain of this, so I have to think about this a little carefully. We have a discontinuity at 0 here, right? And you'll see that here we divided by x, so we introduced a discontinuity at 0. And so this function is not continuous at 0, so this is not a solution for all real numbers. Since our initial x was negative 3, our domain here would be x as long as x is less than 0, be left of that discontinuity. All right, number 2. All right, so we'll do the same thing, put it in its normal form, y prime plus, we'll have 1 over x, y equals 1 over x squared sine of x, and multiplied by our integrating factor, rho y prime plus rho over x, y equals rho over x squared sine of x. And again, we want rho prime to be rho over x, so let's do that off to the side. Rho prime equals rho over x, and we'll set up our separable equation. Oh, well, that's not that interesting. We'll see what happens here. So d rho over rho equals dx over x. All right, integrate both sides. Natural log absolute value of rho equals natural log absolute value of x plus some constant. This means the absolute value of rho is equal to e to the natural log absolute value of x plus c1, just like before. E is equal to, in this case, we can wrap that all into a c, and then absolute value of x. Interesting. So actually, no, that was the whole point of wrapping it into a c, right? Call that c2. Cx, right? We can wrap that absolute value in there. Let's see here. Yeah, because we're going to have, I'm just pausing here for a little bit here because this isn't a solution, and but in this case we have that discontinuity again at 0, and so we can actually clarify it here as well because our initial condition is on the right side of 0. We know this is going to be positive anyway. Alright, so let's multiply that in here. Cxy prime plus Cx over xy equals Cx over x squared sine of x. And we have, dividing by the c's, we have xy prime plus y equals sine of x over x. And the left-hand side is indeed a chain rule, or product rule, excuse me. We have the x times the derivative of y plus the derivative of x, which is 1 times y. The right-hand side is going to be a bit of an issue here. We have an indefinite integral that has no trivial antiderivative, like an antiderivative that we can just do. So we have a problem, xy is equal to this. So here's what we're going to do. We're going to use the fundamental theorem of calculus and say that this is equal to the integral from a to x sine of t over t dt plus some constant where a is greater than 0. So what we're using here, back to Calc 1, you don't use this very often. This is the fundamental theorem of calculus. Notice you're seeing the antiderivative is this function, where if I took the derivative of this function, I would get sine of x over x, and that indeed will happen here. I need a greater than 0 because of that discontinuity there. This is not continuous at 0, and since we want to be to the right of 0, we'll use a being positive because our initial condition is to the right of 0. And so then y will then be, dividing by x, 1 over x. And then this a is just some a greater than 0. So you know what? I'm going to be particular and just choose the same x value that I have here. There's no reason why I have to, but you'll see a little bit later that it does help this process a little bit here. Because the issue is I still need C. And so to get C, we plug in the initial condition, which we could do with any A here, but you'll see that it's easier with this particular A. So to find C, y at 1 is 5, so that means we've got 1 over 1 times the integral from 1 to 1 of sine of t over t dt plus C should be equal to 5. And very conveniently, that crazy integral just becomes 0. And so c must be 5. So now we know the solution is y of x is 1 over x times, unfortunately we're going to have to leave it as an integral, sine of t over t dt plus 5. So that one, is a little bit of an extension. This process right here comes up once in a while where there's no elementary function that we can do here. This one's probably easiest with the power series. But there's no simple elementary function, so we're leaving it just in terms of an integral. And this a here, again, we chose that a to coincide with the initial condition here. And we did that simply to facilitate a convenient c. We did not need to do that. C could just end up being 5 minus whatever this integral is from 1 to 2 or 1 to 5 or whatever, or sorry, from a half to 1 or from 2 to 1 or whatever that particular a was, but it just makes things easier to choose an a of 1. So again, this one's a little bit of an extension, I will acknowledge that, but hopefully you can kind of look through this part over here and have it at least be plausible. So that is it for these two examples. You might want to try doing these on your own and after watching the video and see if you can handle both of these.